last lecture we studied free vibration problems. Specifically, we studied the behavior of two systems. One is damped natural vibration and another is undamped vibration. In damped one, the damping is present, and in undamped natural vibration, damping is not present. Now we specifically took these two systems. This is spring mass system. That problem we have studied, and then another model was that in which we attached a dash part. We attach a dash part here and we put like this. So here, that if we make the free body diagram of this was having kx force, and here, so therefore governing equation was naturally that mx double dot is equal to minus kx, whereas in this system this is mass m and this is kx, and this will basically cx dot. So therefore governing equation was mx dot is equal to minus kx minus cx dot. No external force term was present. Now in this lecture today we are going to study forced vibrations with damping and without damping. Vibrations that take place under the excitation of external forces are called forced vibrations. When we put that this one, when the excitation is oscillatory, the system is forced to vibrate at the excitation frequency. Now what happens that if we see, when we apply a force on a spring mass system, suppose we a mass is there and it is held by a spring, then we displace the mass. Naturally we have created a disturbance from its equilibrium position, so the natural vibrations may start, but the natural vibrations will that is free vibrations, they will decay with time because of the presence of the damping. If damping is not there, then of course these free vibrations will not decay, but because there is a damping, therefore these decay with time, and in any system damping is always present. There is no system in which there is no damping. All systems, because undamped case is just an idealization. Therefore what happens that these vibrations will decay, but because there is a force present that keeps vibrating. So we are mostly interested in the steady state response. Then the system will vibrate with the excitation frequency. If the frequency of excitation coincides with one of the natural frequencies of the system, then we get a condition of resonance in which dangerously large oscillations may result. Large amount of oscillations take place when there is a condition of the resonance. So now we are going to study the mathematical treatment of that forced vibration. French mathematician J. Fourier, who was born in 1768 and died in 1830, showed that any periodic motion can be represented by a series of sines and cosines that are harmonically related. That means that you have a periodic function. Suppose you have a periodic function f(x), it can be represented by a0 plus a1 sine omega x plus a2 sine 2 omega x, like that up to, there may be terms up to so many, up to infinite. Then you have b1 cos omega t omega x plus b2 cos 2 omega x, like that. So cosine and sine terms are there. In a general case, that Fourier, we will not discuss about the Fourier series method. However, that we know that we have any periodic motion that can be represented by a series of sines and cosines. Therefore, the study of forced vibration under the action of a harmonic excitation force is very important, because suppose if we can find out the expressions for that, what happens when the force is F is equal to a sine omega t, then we can take another force F is equal to another a2 sine 2 omega t, and we can so therefore under the action of combine these terms, the response will also be combined, because this is this system, if we take k and m and even damping coefficient c as a constant, then this is a linear system. That means we can simply find out the displacement by superposition under the two circumstances. Now therefore, let us now try to study that this is mass, then this is spring, then this is dash part, and this is x. Now here there is a force F acting here. Now this will be F0 sine omega t. Let us assume that F is equal to F0 sine omega t. That means you have got a sinusoidal forcing function, and this is kx dot this is kx, this is kx, then this is cx dot. Kx is the restoring force and kx is this one. So therefore, what happens that this is now this is the free body diagram of mass m. There is a force F0 sine omega t. This is kx, this is cx dot. Then now consider the spring mass dash part system. The mass is displaced by distance x, and free body diagram is as shown. Now from this figure, we see that the equation of motion is mx dot plus because the equation is basically mx dot is equal to minus kx minus cx dot. So therefore, it can be written plus F0 sine omega t. Therefore, this can be written as mx dot plus kx plus cx dot is equal to F0 sine omega t. Solution to this equation consists of two parts. One is called the complementary function, which is the solution of the homogeneous equation. That means if we solve mx double dot plus cx dot plus kx equal to 0, we will get one solution, that which called solution of the homogeneous equation. This equation mx dot plus cx dot plus kx is equal to 0 is called homogeneous, because if x is equal to a is a solution, then x is equal to a constant times a is also a solution. That means if a one solution is x, then naturally cx is also. So it is totally homogeneous. That is called complementary function. The other one is that particular integral, in which that depends on what is this term on the right hand side. In this case, it is F0 sine omega t. So the combined motion is basically just the combination of complementary function and particular integral. The physical significance of this is that when we displace mass by say some force, then combined effect which we get, that is the sum of these two things. Okay, that means natural vibrations, that mass particle starts vibrating in natural mode, and then there is a forcing term, vibrations are also present. So therefore the motion is the combination of these two. The particular solution in the equation is a steady state oscillation of the same frequency omega as that of the excitation. We can assume particular solution to of the form this one, that just we assume, let us see that what happens. X is equal to, let us say, x sin omega t minus phi, where x is the amplitude of oscillation and phi is the phase of the displacement with respect to the excitation force. If you substitute this expression in the equation of motion, you get like this: minus m omega square x sin omega t minus phi, because x sin omega t minus phi has been differentiated 2 times. So you get minus m omega square x sin omega t minus phi plus c omega x cos omega t minus phi, it has been differentiated 1 time, plus kx sin omega t minus phi is equal to f0 sin omega t. This is sin omega t, or k minus m omega square sin omega t minus phi plus c omega cos omega t minus phi into x is equal to f0 sin omega t. That expression we got. We have to find out the expression for x. Now if we carry out some trigonometry here, can I simplify this expression? K minus m omega square sin omega t minus phi, this is the thing. If we just see that if I can represent them in trigonometric form, that if we say something like that, this is theta, and if I can say something, this is k minus m omega square, and this is c omega, and this is under root of k minus m omega square plus omega square plus c square omega square finally. So then we can get sin theta type of term. So let us see that if we divide that this whole thing by k minus m omega square divided by that thing, this we are dividing this thing by this expression, that means square of these two terms, this and this, then take the under root, we divide by this thing sin omega t. Similarly here c omega t, and here this is cos omega t minus phi, like that, multiplied by, since we divided by under root k minus m omega square by omega k minus m omega square plus c square omega square, therefore we have to multiply it also by this thing, then this expression remains same. So therefore the previous expression and this expression is basically same, this is equal to f0 sin omega t. Now we can take this common here, k minus m omega square whole square plus c square omega square multiplied by cos theta, because this can be written cos theta and this is sin theta, cos omega x is equal to f0 sin omega t, where theta is basically like this, this is k minus m omega square, this is c omega, therefore by Pythagoras theorem this is k minus m omega square plus c square omega square. Now simplifying this expression, we may write this is like that, sin omega t plus phi, because this is the formula of sin omega t plus phi. This one cos omega t minus theta, this is sin omega t plus theta minus phi, basically this is because this is AB, so sine omega t minus phi plus theta. Apply the formula of sine A plus B, so sine A cos B, so sine omega t minus phi cos theta, sine cos omega t minus phi, and sorry, this is theta, this is theta, so this is sine omega t minus phi cos theta, cos omega t minus phi sin theta. So this is like this. So in this expression, this is omega t, this is equal to like that. So sin omega t minus phi plus theta is equal to f0 sin omega t. This expression we have obtained. Now if we compare the right and left hand side of this thing, so this sin omega t, so this has to be equal, omega t plus theta minus phi should be equal to 0. That means we have to say x is equal to f0 by this one, and omega t plus theta minus phi is equal to omega t. This condition has to be, because for all t, if it has to be correct, then this relation has to be satisfied, which gives phi is equal to theta. That means which is equal to basically tan inverse c omega k minus m omega square. We can see tan theta is equal to c omega divided by this thing. So tan omega theta is equal to tan inverse c omega k minus m omega square. We can write x and phi in the, so x is equal to f0 under root k minus m omega square plus c omega square. Now we can write x as f0 by k divided by k, so 1 minus m omega square k whole square plus c omega square by k whole square, and c omega by k 1 minus m omega square by k. It is to be noted that f0 by k is the static deflection of the spring under the action of that force f0 k. Maximum amplitude of the force is f0. So if you apply maximum force, then you will get the static deflection as f0 by k. Now we can put, we know that omega n is equal to under root k by m, that is the natural frequency of undamped oscillation. Now cc is equal to 2m times omega n, which is called critical damping, and zeta is equal to c by cc, that is called damping factor. We can write c omega by k as c by cc, cc omega by k, that means 2 zeta omega by omega n, because cc is equal to 2 okay, cc by cc 2g, and this is cc is equal to 2m into omega n, and m by k is basically 1 by omega n square, omega n square. M by k is equal to 1 by omega n square. So like that we just do that simple. So we will get c omega by k is 2 xi, where xi is damping factor, omega by omega n. Now this gives us x divided by f0 by k is equal to y 1 under root divided by under root 1 minus omega by omega n whole square plus 2 zeta omega by omega n. This is also zeta, this is tan, and tan phi is equal to 2 xi omega by omega n 1 minus omega by omega n whole square. Now why we have written this in this form? As we already mentioned that f0 by k is the maximum static deflection. So x divided by f0 by k gives the ratio of that dynamic amplitude to static, we can say static amplitude or maximum static deflection. And here similarly we get phi is the phase angle, because we assumed that your because we started like this, we assume that the force was F0 sin omega t, but our displacement was sin omega t minus phi. That means there was a phase difference between two. So this gives the idea about the phase difference. Now if we have, in this case, if we see C is equal to 0, then there is no phase difference, there is no damping present, then there is, but if there is a damping present, then there is a phase difference between the applied force and the response we get. So that is the because effect of that damping when it is like that. So because damping also introduces the force. So therefore this comes x is equal to F0 by k under root 1 minus divided by under root 1 minus m omega square by k whole square plus c omega by k whole square, and phi is equal to c omega by k 1 minus m omega square by k. Now this in this is tan phi is equal to c omega by. So using this now notice that in equation this one, in this equation A, F0 by k is the static deflection and x is the amplitude of vibration. So amplitude of vibration can be depends naturally what is the frequency ratio, that means omega by omega n, what is the natural frequency. Therefore the ratio x by F0 by k is often called the magnification factor. How much times the dynamic amplitude is more than the static deflection and depends on omega. Now plots of magnification factor versus omega by omega n have been plotted. We have shown actually for 3 damping values, that is tau is equal to 0.01, that is very low damping, tau is equal to 0.2 and tau is equal to 1. In this case, at omega by omega n equal to 1, if damping is very low, then a resonance type condition occurs. If so we see that the magnification becomes under almost infinity, and otherwise also near this region, near the natural frequencies, the magnification factor becomes very high. However, if we have critical damping, then magnification factor is always less than 1. That means if omega is very high in fact compared to the natural frequency, then damping magnification factor approaches 0. This is very interesting. That means at omega is equal to 0, that means in static case, if you just apply some force and then there will be displacement, and that will be basically x by F0 by k. So therefore you will get the same type of thing, but if we apply that a very high frequency, then displacement approaches 0. Why? Because the mass is not able to respond because of dash part and other things, that because of the dash part it is not able to move at all. So therefore there is this approaches 0. Similarly, but when tau is equal to 0.2, then at resonance it will be very high, but of course it will not be infinite. So if there is a damping present in the system, it will not allow the vibration to become infinite, and therefore but of course that it becomes very high. Similarly, in the case of low damping, it is like this. So let us just see. Now when the damping is very small, the magnification factor is very large in the vicinity of natural frequency. Hence, the forcing function should not be close to natural frequency if the vibrations have to be avoided. Now, for very large value of omega by omega n, the magnification factor becomes very small. Hence, the operating or forcing frequency should be 4 to 5 times the natural frequency for best results. That means, if you have the natural frequency of some system is 100 hertz, if you have the forcing function frequency at 400 hertz, then you know that it will not. We might have noticed these type of examples, like a fan makes lot of noise when it is run at a low RPM, but when the RPM is increased, then it does not make that much noise because of this phenomena. Similarly, some cars also, when they run at a low speed, then they will show vibrations, but at high speed the vibrations are not seen. So this is the this one. Now for undamped forced vibration, now undamped one damping factor zeta is 0. Thus we get x is equal to f0 by k 1 minus omega by omega square, and we get phi is equal to 0. There is no phase difference between the forcing function and the response. Now then we are getting this type of expression. Here also it is seen that if omega is very small, then x is equal to, of course, f0 by k, but if omega is very large, then this x will, capital X will approach 0 because of this term f0 by k. So this term will approach 0. So f0 by k divided by 1 minus omega by omega n square. This term approaching infinity, you get something like here 0. So this is the interesting thing. So if you, that means if you have a spring mass system, like this, there is a very flexible spring. If you apply a force of a very high frequency, it will not be able to move. That means it will not carry out any vibrations. So this is the thing, that it is like this. Now complementary solutions known as the transient solution is of no special interest, since with time it dies out with a small amount of damping which can never be completely eliminated. Therefore, we have not discussed about the complementary solution, which are called transient solution. This is of no special interest. However, in undamped case, one can study actually and this one, and one can get some insight about and the cases in which damping is almost 0. Now let us discuss the other type of that problem, that is the problem involving the support motion. What is this? That if you have kept this on a support, this is a support, this is a fixed support like this, and this is mass, and this is spring, and this is dash part. Now support itself is getting excited, support is being excited, and support is undergoing the displacement y, and mass itself is undergoing that displacement x. This is the equilibrium position of the mass, and it is x is the displacement from this position. So this will be let y be the harmonic displacement of the support point. Now if we measure the displacement x of the mass from an inertial reference, we can make from the free body diagram of the mass. Now it is subjected to spring and viscous force. Now equation of motion, so is like this. This is mass, it is stress. Suppose you have pulled the mass by amount x, but the support by that time also has moved by a distance y. So net stretching of the spring is kx minus y. Therefore the spring will provide a force kx minus y in this direction. Similarly, the net velocity of the mass from a inertial reference frame, means from outside outside observer, which is on a maybe fixed frame, which is all from that frame he is observing, and he says that net velocity of the mass is x dot minus y dot. Okay, this is okay, this one is that this is the velocity, that is the relative velocity, because otherwise the our absolute velocity of the particle is x dot, mass m is x dot. So therefore this is, and support itself is moving with y, this one. So therefore net velocity is relative velocity between this thing is x dot y dot. So that means dash part is there. So dash part's piston is moving with x dot, cylinder itself is moving with y dot. So difference is x dot minus y dot. So therefore cx dot minus y dot is equal to kx minus y. Now put z is equal to x minus y. If we put z is equal to x minus, so we get mx dot by first Newton's law gives mx dot is equal to minus k x minus y minus c x dot minus y dot. Now we are getting the terms x minus y, so therefore better to write it like z, some the variable gets reduced like that. So you say z is equal to x minus y, we get mz double prime, because okay, so here we don't have any y term. So if we put that here also mx dot minus y dot, then since we have added here, so therefore from here we can subtract that thing, we can add here also, so it becomes minus my dot. So therefore it becomes mz double dot plus cz dot plus kz is equal to minus my double dot, and this is y is equal to, if we assume that support is getting excited by y is equal to y sin omega t. So therefore this is minus m omega square y sin omega t. So you are getting this thing. So it is a solution can be immediately written as z is equal to z sin omega t minus phi. This, because this type of thing we have already done, this is like a force, instead of the force f0 sin omega t, now we are having m omega square y. So m omega square y is like a force. So z is equal to z sin omega, and z is equal to m omega square by y under root k minus m omega square whole square plus c omega square, and tan phi is equal to c omega k minus m omega square. Now it is this one. If we see that in this case, if the frequency ratio omega by omega n is large, then z by y becomes equal to 1 for all values of the damping ratio. That means that let us discuss this point little in detail. That we have, see, m omega square tan phi z is equal to m omega square y under root k minus m omega square square plus c omega square. Now tan phi is equal to c omega k minus m omega square. In this case z by y is equal to 1 for all values of the damping ratio. This one, how we can prove this? Z is equal to, let us write z is equal to omega by omega n is large. That means let us say that z is equal to m omega square y divided by k minus m. So we take that, maybe we can take m square common, so m can be taken common here. This becomes k by m k by m minus omega square whole square plus c square omega square. This is equal to m omega square y. This is m, and this will become k by m minus omega square. So this is under root omega n square minus omega square whole square plus c square omega square. Now omega by omega n is very omega n by omega n is large. That means omega n is smaller, much smaller in fact, in comparison to omega square. Therefore here omega n square minus omega square can be written as omega square only. So this will become omega to the power 4, and this becomes m omega square y divided by m under root omega to the power 4 plus c square omega square. Now since omega is a very large number, omega 4 term is very high in comparison to c square omega square. First of all, damping is always less than 1 and omega. So therefore what happens, this I can write as m omega square y divided by m omega square, that is m omega square. So this is equal to y. So therefore z is equal to y. So irrespective of damping, z is equal to y if omega by omega n is large. That means if the support is being excited by a very high this one, so then z will be equal to y. But then what happens, z is equal to y, but z is basically x minus y. So that means we have said z is equal to x minus y. So yeah, that is equal to y. So what happens, that z by y is almost this one. That means the relative that displacement is almost same as that, you know, that support displacement. So this is the thing. So now using the characteristic of that this type of response, that you know that we have got response for magnification, and understanding that we can design various type of systems. You know what is our primary interest. Sometimes you have to design the system for measuring the acceleration. Sometimes you have to isolate the vibrations. So these type of things are there. Now let us discuss. So this briefly we have discussed. Now let us discuss one or two other interesting things. Now this factor which you get, you see here, f0 by k 1 minus omega by omega n square whole square. If omega by omega n becomes equal to 1, this will become 0. So this factor is 1 by 1 minus omega by omega n square is called resonance factor. Rho, we can denote it by rho. So therefore if omega is equal to 0, resonance factor is 1. If omega is equal to very large, resonance factor is 0, and if omega is equal to omega n, resonance factor is infinity. Now we have seen that you perhaps get the idea that at omega is equal to omega n, that amplitude of the vibration becomes very high. Now let us solve the differential equation when there is a resonance we know that the differential equation, that suppose the mx dot plus kx is equal to kt, say x, okay, kx is equal to f cos omega t. Let us say omega is omega n, so omega nt, and this can be written as x dot plus k by m x is equal to f by m cos omega n t. Now k by m is equal to omega n square. Hence, x dot plus omega n square x is equal to f by m cos omega n t. This is the differential equation which has to be solved. Now here we can see that if we just put x is equal to a sin omega t, that will not satisfy this differential equation in this case, because this is the thing, that is therefore in this particular case, when you are getting that same omega n here and omega n here like that, so therefore you will a particular solution in this case is yp xp is equal to t times a cos omega n t plus b sin omega n t. That is the thing. And for this now we can have, these are the constants. Now we have can have cases. Now let us see what happens that when x is equal to 0 at time t is equal to 0 and x dot is equal to also 0. That means displacement and velocity, both components are 0. So what will happen, that this will become at t is equal to 0. So let us write the solution again. X is equal to t and this is a cos omega n t plus b sin omega n t. Now at t is equal to 0, okay, x is equal to 0, x is equal to 0. Now let us see x dot is equal to a cos omega n t plus b sin omega this one. So we have to put that condition, and after that we will get that some solution which will be equal to xp equal to f0 divided by 2m omega 0 t sin omega 0 t. So that means at natural frequency the vibrations will always keep increasing. So this is amplitude of vibration will always keep increasing. So this type of phenomena will come. Okay, this is like that. So with time the magnitude always keeps on increasing. This is what that we observe. So this is the type of this one resonance. So this condition has to be avoided, and let us now see that if in case damping is very small and your omega is very near to this one omega 0, that means omega is almost omega n, then x is equal to f0 divided by m omega 0 square, this is omega n square minus omega square cos omega t. This is the particular integral, and this can be written as f0 divided by k 1 minus omega by omega n whole square, and this is cos omega t. Now here, therefore x is equal to, now we consider that even the if there is no damping, let us take the case of no damping, then there will be a homogeneous solution also, that will be, that is the complementary part. So complementary function is given by c is a constant cos times omega n t minus phi. Therefore, where phi is some angle, therefore x is equal to c cos omega n t minus phi plus f0 divided by m omega 0 is omega n square minus omega square cos omega t. This term has come like this, and if in this we put the condition that at time t is equal to 0, x is equal to 0, at time t dot t is equal to 0, x dot is also 0, that means we are applying the forcing function at the time when the particle is at rest, and from that equilibrium position, then I will not show that required algebra, then these c and phi can be eliminated, and then you get x is equal to f0 divided by m, and this will be equal to omega n square minus omega square, this is cos omega t minus cos omega n t. So this will be, this can be written as cos omega t minus cos omega n t. We have the formula for cos c minus cos t. So this can be written as x is equal to 2f0 divided by m omega n square minus omega square sin omega 0 plus omega divided by 2 into t sin omega 0 minus omega divided by 2 into t. This is the thing. So we get so if we plot this thing here, the plot may look something like this. And then again it goes like this, it is. So what happens that we will, because omega 0 minus omega, it will is very small, so therefore this time period will be very large and we will get the phenomena of beats type of thing. So here we will be getting the beats type of thing. So this is about this thing. So like that we can actually study the different type of problems. And now okay, so we will conclude here. So today I have discussed about forced vibration problem, in which we consider damping and this one. Now let us consider the cases you will always not getting a spring mass system. Say sometimes you have got the axial rod. Now if you have got axial rod and you are applying a force, here there may be a mass, you are applying a force here. Even this type of problem can be solved by a spring mass system. So you model it like a spring and this is the mass. Some portion of the rod mass can also come here and it can be lumped at that point and then it becomes like that one. Now here, supposing you are applying the displacement, this is the force, this is a rod of length L, this is the force. If you apply a force F, cross sectional area is A, so therefore this will give stress is equal to F by A and strain is equal to F by A divided by A times E. E is the Young's modulus of elasticity. Therefore therefore displacement delta of the end point is equal to FL divided by AE. This F by delta is called stiffness K, that is equal to AE by L. So you see that in this case the spring constant can be written as AE by L and you can actually solve this problem. So axial vibrations of this system will be more, this one having more frequency if that A is more and this is a thing. So similarly, if you have say some cantilever beam type of thing here and if you apply some load delta here, okay, so you have see that F is equal to PL cube by 3EI, delta is equal to PL cube by 3EI. This is known from the strength of material. You will come to know about that thing experimentally. Otherwise what happens, take a cantilever beam, apply some force, measure its deflection, then you know that one can plot P versus delta. P is the force here and that slope of this gives you stiffness dP by d delta. So therefore here is stiffness. So therefore as the length increases, its stiffness decreases. Therefore you can do that one simple experiment you can make, that you take a beam type of thing and here you between two adjustable clamps you put it and clamp it properly from some screw here. So you can always see that when the length was large and if you displace it slightly, you can observe its natural vibrations. It will vibrate with a longer time period that means less frequency. And if the same thing you displace and you make like this thing has been displaced this side, and now you have like this, it is here, and if you vibrate, then the frequency of vibration will be very high, and this is how that it will be doing. So therefore these type of simple experiments one can do and one can observe. So this is the thing. Now in the next lecture we will discuss the vibration of the rigid bodies.